So here's the unit circle. The unit circle has the center at 0, 0 and a radius of 1. And in particular, over the next little bit, we're going to use two of our big ideas from the unit circle. One of the big ideas that anytime you have coordinates on the unit circle, the x coordinate is cos theta, the y coordinate is sine theta. And secondly, tangent of theta is sine theta divided by cos theta. So what we're going to look at is certain families. The first family that we're going to look at is the axes family. The axes family includes all the points on the axes. Now, if you look at the first point on your axis, that would have an angle of 0 degrees, or 360 degrees. Would you agree that if you ended at the positive x-axis, that would either be 0 degrees or 360 degrees? If you went to this point at the top of your circle, the angle would be 90 degrees. So what we're doing right now is we're color coding all of our angles in degrees. Then we'll put those same angles in radians. We'll label the coordinates, and we'll figure out tangent. And we'll see how powerful this is. Would you agree that this is 180 degrees? 3/4 of the way around is 270 degrees, and then, of course, all the way around is 360. And I mean, we could keep going if we wanted to say more coterminal angles, but we'll just go once around the circle. Switching colors in radians, 0 and 360 would be 0 and 2 pi. Probably the next easiest one to do in radians would be 180 degrees. How much is 180 degrees in radians? Pi. So then what is 90 degrees? Pi over 2. If it's half of 180, it's half of pi. And 270, well, if this is pi over 2, 2 pi over 2, this will be 3 pi over 2. If the radius of this circle is 1, what's the coordinates of that point? What's the y coordinate? 0. What's the x coordinate? The radius is 1. How many units would I go if I went over this way? 1. And if the radius is 1 and I went to this up here, it makes sense that you'd have the coordinate 0, 1. Now I go 1 to the left. Negative 1, 0. And finally, 1 down, 0, negative 1. And this is where the unit circle and our big ideas start to become really powerful. Who do you think wants to be our first volunteer? Nobody? Raiden, you look around. Who do you think wants to be the first volunteer? You get to pick. Oh, I like either he looks one way, people either avert their eyes or shake their head furiously. But you have to pick someone, or it's going to be you. Okay, Gavin's first. So now the question I'm going to ask is, looking at this, you can now do sine and cos of a bunch of different angles without your calculator. We'll start with 90 degrees. What's sine of 90 degrees? 1. How do we do that? Well, our big idea says that coordinates on the unit circle are cos, sine. If I say sine of 90 degrees, here's 90 degrees, I look at my coordinates, sine of 90 degrees is going to be the y coordinate. Sine of 90 degrees is 1. If I said, what's cos of 3 pi over 2. Gavin, you get to pick the next volunteer. Sorry, who? Okay, so now we're going to 3 pi over 2. We're doing cos. So which coordinate are we going to look at? X coordinate. 0. Perfect. And so we can do these values, mental math, just by knowing the circle. Right? Sine of 360 degrees. 0. Cos of pi. -1. So the answers are all in the coordinates. And then, if we know that tan is sine over cos, I can figure out what's tan of 0. Tan of 0 will be sine, which is 0, divided by cos, which is 1. Tan of 0 will be 0. What's tan of pi? Sine divided by cos, 0 divided by -1, 0. What happens when I do tan of pi over 2? Sine 1, cos 0. What's 1 divided by 0? It's not 0. Undefined, not possible. It's not possible. So you can either write undefined or you can write not possible. The same thing is going to happen at 3 pi over 2. Tan of 3 pi over 2 is not possible either. We're not allowed to divide by 0. There's a picture here of what happens. You can look at it later. Someone who divided by 0 at their house and everything exploded, and it's like not good. That's our first family, the axes family. Now our second family is looking at all of the 45-degree family. What makes something a family, again, is based on reference angles. For the 45-degree family, all of these points on the unit circle have a reference angle of 45 degrees. So in quadrant 1, again, what color did I pick for degrees? I picked blue. So in quadrant 1, this angle would be 45 degrees in standard position. What angle would I have in quadrant 2 with a reference angle of 45 degrees? (135 degrees). How would we find that? Well, this angle would be 180 minus 45. Quadrant 3. (225 degrees). 180 plus 45 degrees. And then quadrant 4, you'd have to go 360 minus 45 degrees. 315 degrees. In radians, 45 degrees is pi over 4. We need to find out what 135 degrees is. So we have a couple of options. One option is we could change 135 degrees to radians using the formulas that we had. So you could do 135 multiplied by pi over 180 and simplify that. Okay? The other option is to think, well, I found 135 degrees by doing 180 degrees minus my reference angle. If I'm thinking in radians, I could find this angle by going pi minus my reference angle. But then we're dealing with fractions. How do you subtract fractions? You need a common denominator, which in this case, we have pi over 1. We'd have to change this pi to be 4 pi over 4 minus 1 pi over 4. And our angle would be 3 pi over 4. And sure enough, if you had reduced this over here, this would be 3 pi over 4 as well, but I don't think this is quite as easy. It's easier to think about using your reference angle. What about in quadrant 4? Instead of subtracting your reference angle, you'd add your reference angle, giving you 5 pi over 4. And here, now you would have to go 2 pi minus your reference angle, get a common denominator, (8 pi over 4 minus pi over 4). Adding and subtracting fractions, another thing this year that you're going to get really good at because we have to do a lot of mental math that way. So now we have all of our angles in radians as well. Now we have to find these coordinates without a calculator. So we have to figure out where those things are going to be on our unit circle for 45 degrees, 135 degrees, and so on. And so in this space on your paper in the bottom right here, special triangle for 45 degrees. If you draw, again, we're dealing with sine and cos and tan. What kind of triangles have sine, cos, and tan? Right angle triangles, right? Sine is the opposite over hypotenuse. So what we need is we need a right angle triangle with one angle being 45 degrees. What's the other angle going to be? We've got 90 here, 45 here. What's the top angle going to be? 45 as well. Why? Because it all has to add up to 180 degrees. Now, that's a right angle triangle, but when both the angles are the same, there's a special name for that as well. What kind of triangle is that? Isosceles. And what's special about an isosceles triangle? Two angles are the same and two sides are the same. So this side here and this side there are going to be the same. And the powerful thing about trigonometry is that the ratios stay the same no matter how big or how small the triangle is. If you have any triangle for 45 degrees, and you type into your calculator what's tan of 45 degrees, it's going to tell you it's 1. Why is it going to be 1? Well, tan is the opposite side over the adjacent side. What do we know about the opposite side and the adjacent side? They're both the same. So if both numbers were 10, 10 divided by 10 is 1. If both numbers were 7, 7 divided by 7 is 1. As you can see, I've practiced dividing numbers that are the same, like last night, for hours, just so that today in class I'd be prepared. And if you pick a number, any number for this side, test me here, see if I practiced it. 8. 8 divided by 8, 1. Okay? So it doesn't matter what the two sides are, right? Tan of 45 degrees is going to be 1. And it won't matter what the sides are sine of 45 degrees is always going to be the same. But to find that out exactly, we need to put a number for these sides. And it's not going to matter which number we choose, so I'm going to just choose 1 and 1. How long is my hypotenuse? Square root of 2. Excellent. And if I label all three of those sides, we've already talked about tan of 45 degrees is equal to 1. But now I can say sine of 45 degrees is equal to, actually I want to write these underneath. There we go. Sine of 45 degrees is equal to 1 over the square root of 2. And if you rationalize the denominator from grade 11, where you multiplied top and bottom by root 2, are you okay that I write this as root 2 over 2? Those are the same things. And cos of 45 degrees would also be 1 over root 2, which is equal to root 2 over 2. If you type in root 2 over 2 in your calculator, you will get 0.707 with a whole bunch of decimal places after that. If you type in sine of 45 degrees into your calculator, you'll get 0.707 with a whole bunch of decimal places after that. They will be identical. Sine of 45 degrees is root 2 over 2. Don't write this down. Right? You tested me with 8. Okay? I successfully did 8 divided by 8 to be 1. 8 squared plus 8 squared, 64 plus 64, 128. Right? This side will be the square root of 128, which you could divide by 64. You okay that that's 64 times 2, which as a mixed radical is 8 root 2. Are you okay with that? So now, what's sine of 45 degrees using this bigger triangle? It would be opposite over hypotenuse. Can you see that your 8s could simplify? We get the exact same answer. It would work if you had chosen a much bigger number. Thank goodness. 8 was, I practiced up till 9 last night, so got all those numbers in. But you pick any number and you simplify it, you will get 1 over root 2 or root 2 over 2 for sine of 45 every single time. So what's the power of this? I'm going to erase this blue part. We can take these numbers and now we can go to our unit circle and say the big idea of our unit circle is the coordinates are cos theta comma sine theta. So my coordinates here are root 2 over 2 and root 2 over 2. Then I go to this point in quadrant 2. Can you see that it's exactly the same height as that point? I mean, it's the same, like, again, don't draw this in, but this triangle here is my special 45-degree triangle. It's identical over there. Those two triangles are the same. And so my y-coordinate obviously is going to be also root 2 over 2. What's my x-coordinate going to be? Negative, because you're going left, right? It's going to be negative root 2 over 2. And this one down here, negative root 2 over 2 and negative root 2 over 2. And finally here, your x-coordinate would be positive, your y-coordinate would be negative. And if we write tan of pi over 4, or 45 degrees, we already know that that's 1. When you go to 3 pi over 4, again, it's the same triangle, so opposite over adjacent is still going to be 1. But since the big idea says tan is sine divided by cos, if I did root 2 over 2 divided by negative root 2 over 2, I'm going to get tan is negative 1 in quadrant 2. And in quadrant 3, it's going to be 1 again. But if I did sine divided by cos here, I'd get positive 1. And finally, in quadrant 4, I'd get negative 1 again. And all of a sudden we're seeing, do you see how the big ideas of the unit circle explain the cast rule? What does the cast rule say in quadrant 2? Only sine should be positive. Sine is which coordinate? The y coordinate. Makes sense. The x coordinate's negative. Big idea, tan is sine over cos. Well, a positive number divided by a negative number is going to be negative. Tan will also be negative. Quadrant 3, can you see that both the x and the y are both negative? In quadrant 3, both sine and cos are negative. But tan is the one that's positive. And if we use the big idea that tan is sine divided by cos, we get a positive number. And now we can do some mental math. Gerard, it's your turn to pick a volunteer. I want that volunteer to tell me what cos of 3 pi over 4 is. Negative root 2 over 2. So cos is your x coordinate. 3 pi over 4, negative root 2 over 2. Okay, Theo, pick a volunteer that's going to tell us what sine of 315 degrees is. Eljon. Sine of 315 degrees. Negative root 2 over 2. And finally, last volunteer, for cos of 5 pi over 4. Negative root 2 over 2. Cos, quadrant 3, negative root 2 over 2. Excellent. Okay, ready for the next family. The 30-degree family. So now, all of our reference angles are 30 degrees. You have a 30-second head start to finish the other 3 angles. How did you do? 150 degrees, 210 degrees, 330 degrees. In radians, 30 degrees is pi over 6. Have a 30-second head start to finish the radians. How did you do? did you get? 5 pi over 6, 7 pi over 6, and 11 pi over 6. Again, in quadrant 2, I would think of pi minus my reference angle. And for my common denominator, you'd change pi to 6 pi over 6, minus 1 pi over 6, 5 pi over 6. 6 pi over 6 plus 1 pi over 6, 7 pi over 6. And 2 pi would be 12 pi over 6, minus 1 pi over 6, 11 pi over 6. Now for our coordinates. For our coordinates, we need another special triangle. So again, what I'll get you to do in this space right here, special triangle. Wow, that doesn't look like a triangle, that looks like an A. Here we go, special, there we go, triangle for 30 degrees. And I'd like you to draw it with the 30 degrees up here. If that angle is 30 degrees, what's the other angle? 60 degrees. And just looking ahead, that's my next family, so that becomes a special triangle for 30 degrees and 60 degrees. That triangle is a right triangle. Are any of the angles the same? No. Are any of the sides the same? No. What's the name of this triangle? Scalene. It's the triangle that you forget the easiest, because it's the special name they gave triangles that aren't special. There's nothing special about it. It's got all different sides, all different angles. We don't know anything about this triangle. It's called scalene, but it's really not special at all. And so this poor triangle was walking down the hallway, feeling bad, feeling I'm not special at all. Runs into another scalene triangle, looks like they're exactly the same. And that other scalene triangle, same thing. Yeah, I'm not special either. So they're like, well, maybe we should become friends. So these two not special triangles became friends. So I'm going to draw the other one right here. And together, they became something special. What happens if I put those two not special triangles together? The whole thing all has 60 degrees. What kind of triangle is a triangle that's all 60 degrees? Equilateral. What do we know about an equilateral triangle? All the sides are the same. Again, we could pick any number here, but I'm going to choose this side is 2, this side is 2, and the reason I chose 2 is how long is this side on the bottom going to be then? The blue and the green. Has to be 1. Oh, I want that one blue. That one. Why? Because together it would have to be 2 in order to make it an equilateral triangle. And if I can do that, I can figure out how tall this is by doing a squared plus b squared equals c squared. 1 squared plus something squared equals 2 squared. This side has to be square root of 3. Again, our mental math with a squared plus b squared equals c squared is going to get really good. And once you've labeled all those sides, well, now we can say, I know what sine of 30 degrees is, what cos of 30 degrees is, and what tan of 30 degrees is. Sine of 30 degrees, opposite over hypotenuse. 1/2. Cos of 30 degrees, adjacent over hypotenuse, √3/2. And tan of 30 degrees, opposite over adjacent, 1 over the square root of 3. And if you rationalize that, you'll get square root of 3/3. So again, if you were asked what's the exact value of tan of 30 degrees on a test, it would be correct if you wrote 1 over the square root of 3, or if you wrote the square root of 3/3. Both answers are fine. And because this also has 60 degrees in it, we also know what sine of 60 degrees is, cos of 60 degrees, and tan of 60 degrees. Sine is opposite over adjacent. Cos is adjacent. Oh, sorry, opposite over hypotenuse. Cos is adjacent over hypotenuse. And tan is opposite over adjacent, which would be √3/1, but I'll just write square root of 3. Now we can use our big idea and say points on the unit circle are cos comma sine. So if I am labeling this point right here, cos of 30 degrees, √3/2, sine of 30 degrees, 1/2. 30-second head start to finish the other points. How did you do? The points stay the same because if we drew those triangles with the same reference angle, they'd be exactly the same. Opposite over adjacent would stay the same all the time. Opposite over hypotenuse stays the same all the time. We know that tan of 30 degrees, or tan of pi/6, is √3/3. We now know that tan of 5 pi/6 is negative √3/3. Tan of 7 pi/6, positive √3/3, and tan of 11 pi/6, negative √3/3. And we could do mental math like we did before. We could say, what's sine of 11 pi/6? Who's the last person? Charles? You have to pick a volunteer. Okay. Sine of 11 pi/6. Negative 1/2. Okay. Cos of 5 pi/6. Race and pick some. Parker. And because it's here in quadrant 2, it would be negative square root of 3/2. So if we have the circle written out, we can get the values very quickly. I'm not sure if you have things that, if you remember how you remembered them in grade 11, but you're going to find that this will allow us to memorize them even easier and even quicker, right? Grade 11, you might have still used the special triangles. You might have seen those triangles in order to create them. But now that we'll put these values on a circle, you're going to find there's a lot of things that make memorizing them easier. But before we get to all of that, we've got one family left to do, which we've done most of the work for. Okay? So degrees, this is every family that has a reference angle of 60 degrees, or in radians, pi over 3. We've already done the special triangle. We know that cos of 60 degrees is 1/2. Sine of 60 degrees is root 3 over 2. I'm going to stay consistent. I've done radians every single time here. Tan of pi over 3 is root 3. I'll give you a minute head start to finish the whole thing. Well, there are all the values so that you can check to see how you did. And we can do some mental math. What's tan of 240 degrees? Parker, you get to pick the next volunteer? Joseph. Tan of 240 degrees. Square root of 3. Cos of 60 degrees. One half. Sine of 5 pi over 3. Aaron, who are you going to pick? Yeah, you can pick Raiden. He started this whole thing, but he hasn't answered yet, so it's fair game. Perfect. Sine of 5 pi over 3, negative root 3 over 2. So we start to see that it's really important that we have the big idea of the x-coordinate being cos of theta and the y-coordinate being sine of theta, because the data's here for us to be able to do that mental math quickly. The next thing we're going to do is get all of this data onto one circle, and then with that, we're going to make our unit circle project. So that's the next thing I'm going to introduce.